Okay, we should be live. If there's any technical details, technical difficulties, don't hesitate to send a message on the live chat. Welcome to the first set of talks from the speaker series at Warwick Artificial Intelligence. Warwick Artificial Intelligence is a society at the University of Warwick, which aims to inspire, educate, and connect students with artificial intelligence. If you're interested in giving talks as well, and you're a student, then feel free to message us, and we'll get in touch, and we'll be more than happy to have you talk about what you're passionate about in artificial intelligence. So today, I'm Chanon. I will be talking. I will be giving the second talk, and the first talk today will be given by Neel, who will be talking about how AI is revolutionising the world of finance. So following from the AGM we had yesterday, we will be posting on our social media and our website available roles. So do have a look at those. And if you're interested, some of the roles, you don't have to know much artificial intelligence at all. Some of them may be a bit more intensive, but keep an eye out for those. So we'll head. I will hand over to Neel.
Thank you, Shannon. We'll just get right into it, and I'll give you a brief background as to why I'm covering this topic. I feel any kind of technology is serving either two purposes. It's either solving an existing problem, or it's optimizing something that already exists. And I feel I'll give a much greater impact by talking about the fundamental problems that actually exist in banking and finance, and how AI can actually help solve that. The first one is the fact that there still exists stuff like transaction costs and various kinds of fees in today's banking world. It is quite astonishing that it exists right now, mainly because of the fact that the biggest services and the biggest companies that exist right now, all of them give out free services. Like, for example, Google, which is a free search engine. And it's pretty astonishing. We have stuff like Google Maps, which is a GPS, which is given to you for free. And AI, to an extent, can help solve that problem. And I'll talk briefly about that later on. The second problem is the fact that there exists banking fraud to this day, despite so much money being poured into compliance and so much regulation already existing. The third is bureaucracy. Now, this is not necessarily an increasing problem in the West and in the developed world, but it's a major hurdle in the developing world, especially with the likes of India and other emerging economies like Nigeria and stuff like that. I feel AI can have a much greater impact in the developing world when it comes to reducing bureaucracy and reducing processing times when it comes to opening a bank account and simple tasks that shouldn't be so complicated and shouldn't take so much time. To an extent, in the West, this is already being done, and I'll briefly talk about that as well. The last is need for personalized finance. A lot of the services that you already have give you personalized, tailor-made services for free, but that is not widespread in banking. And also, even if it is, it results in higher operating costs, which brings us to our very first problem. So the first problem, how can AI help reduce operating costs, and as a trickle-down effect also help reduce transaction fees, etc.? AI fundamentally can help eliminate the need for humans at lower levels of the bank. And people at times do say that AI can help, will destroy jobs and stuff like that. But the way I look at it is that it's destroyer of jobs, creator of better ones. AI can help reduce the need for call centers to solve minuscule problems and humans to be involved in activities that are not intellectually stimulating and don't really add intellectual value. Stuff that can be carried out easily by artificial intelligence, which is pretty standard and something that artificial intelligence won't take a lot of time to learn. In effect, this will help reduce a lot of the operating costs, mainly because AI can help function 24/7, and over time it will help reduce the setup costs that actually are involved in AI. And essentially, data is fuel for AI, machine learning algorithms. Hence, with time, these machine learning algorithms will only get better. But there's a small catch. The catch is that you need to set parameters when it comes to artificial intelligence technologies and algorithms. Hence, if there is a very unique problem that you have or a very unique complaint that you have, artificial intelligence might not be very effective at tackling it at first. Something that is very odd and not something that is in the ordinary, or not something that is designed to actually solve effectively, at least earlier on. Hence, there'll be a degree of human intervention required when it comes to things like solving problems. But this will reduce over time as there is again more data being fed into the machine learning algorithm. The second is banking fraud and compliance. And as I said earlier, it is surprising that it should astonish us that it costs big banks with the likes of Deutsche Bank, BNP, HSBC, costing them millions, if not billions, of compliance and compliance penalties and fees every year, when there is existing compliance measures, there's existing comprehensive regulation, but cartels and the underworld find a way to go around it from time to time. And machine learning and artificial intelligence have proven to be more effective in finding out payments frauds and fraudulent scams. And implementing these on a wider scale will not only make things better for customers, not only reduce incidents of payments fraud, but it will also help make things much more faster and much more efficient, since AI can work well with big data. Hence, when it comes to global databases, artificial intelligence can optimize whatever it is that you need to verify. Now, the third one, which is reducing bureaucratic footholds. Moving on from the last point that I covered for the last problem, the fact that it can process huge amounts of data very effectively also means that it can verify identification, ID checks and stuff like that very easily and very quickly. And the reason this is important is because of the fact that even today, trading accounts and bank accounts take a few days to actually activate. So let's say if you wanted to buy GameStop, and if you wanted to buy it right now, and if you didn't have a trading account, let's say, it would take you anywhere between a day or two to actually set up a trading account. And by then, it might already be too late to actually buy the stock. And I personally haven't received verification for one of the apps that I signed up for last week. So this artificial intelligence can help optimize this. It not only can it make it faster to verify ID, but also it is more effective in finding out fake IDs and ID scams. And identity theft is another billion-dollar problem which AI can help solve. Hence, I feel this is another area that artificial intelligence used in banking and finance can really help optimize our current existing protocols. One of the points that I didn't mention in the first slide when it comes to problems is the need for human intervention in making credit decisions. This is a fundamental problem and has been for quite a while, because there still exist discriminatory practices on the basis of race, sex, religion when it comes to lending out money from banks. And this shouldn't really be a factor anymore when we are in 2021. Hence, AI will help reduce the need for that. it will make this much less discriminatory and much more fair for everyone involved. And not only that, but also the fact that there's existing automation when it comes to credit lending and borrowing in banks. But AI will help optimize that in the sense that it will be constantly being fed data and will constantly assess credit risk within banks. And it will avoid banks from over lending or over borrowing. And that is another way that has been rather unexplored by banks that could actually help banks optimize their returns on investments. Moving on, making personalized finance accessible. Now, fintech has been one of the key sectors that have dominated in the last few years, when we have the likes of PayPal and Square surging in our share values, and there being a very positive sentiment around the growth for these companies. Now, deploying artificial intelligence to personalize banking and digital banking, it will help in the way that if you have, let's say, existing goals, existing financial goals, let's say you want to save this much money at the end of this year, or let's say if you want to go for this holiday at the end of this year, AI in personalized banking apps will act as a sort of a finance manager, a finance assistant, where it will constantly reiterate how much you need to save compared to how much you have in your bank. And it will assess your cash flows over time and assess your spending patterns over time and assess what you must buy and what you must not, what you must avoid to eventually reach your goal. And I feel this is one of the things that will catch on in the next few years. This is already being used by very select few fintech companies, but it's not as widespread as it should be right now. Hence, I think this is one of the areas where there is a lot to be achieved. Now, lastly, AI in algorithmic trading and financial instruments, basically. Essentially, algorithms and artificial intelligence, if you were to ask around 15 to 20 years back in like financial instruments, people would say it's only used by select few hedge funds. And one of the most remarkable ones was the Medallion Fund used by Renaissance Technologies, which has generated anywhere between 20% to 98% returns from 2002 to 2016. And it's been one of the most successful hedge funds, mainly because it has caught on to the trend earlier than its competitors. But now that there is extensive libraries in Python and the fact that a lot of its Python syntax is rather easy to use, it is making retail investors actually catch on to this trend as well and access higher returns than they normally would. And it's in a way shifting the power dynamic. I would say GameStop is sort of a symptom of that, where the power dynamic of your common retail investor and your big institutional investor is changing. This will help exaggerate that in the sense that if you were to make a AI-based trading bot right now, you require a very brief knowledge of Python because there exists, as I said, loads of extensive libraries which can help you make your own AI trading bot. I feel this is fundamental in the sense that a lot of people will take responsibility for the investments they make for themselves. And again, the GameStop incident was another result of what happened in the 2008 crisis, where there was after which there was huge distrust in financial institutions that handle people's money. Hence, I feel this is a very critical aspect and something that is in the run right now, but it's, again, as I said, not quite widespread. And I think this will pick up in the next few years. So yeah, that's about it. There's a few references regarding what I've said and a few details. I feel if you want to go through them, feel free to go through them. We've given the title and the author's name, so it should be relatively easy to find on Google. And yeah, that's it from my side. Over to you, Chanon.
Okay, thank you, Neel. So where do you see the future of finance going generally?
That's an interesting question. I feel the future of finance is more decentralized. So how I ended with the fact that the power dynamic is shifting, how it's becoming less centralized, and people are taking responsibility for their own money, and even I would say even blockchain technology to an extent will help exaggerate that. With when you have concepts like decentralized fund, DeFi, and smart contracts and stuff like that. So I feel in the next 5 to 10 years, if such technologies do catch on, people do actively educate themselves about these technologies, we can have a more widespread use of these technologies. It's going to happen eventually, but it's a matter of how quickly it can happen. And I feel the quicker the better, because that goes with any technology for that matter, because it helps solve a lot of problems.
Okay. Do you think there are any possible dangers? I mean, there must be, right?
Dangers. I feel like at least like when it comes to stuff like algorithmic trading and AI trading, I feel people can get carried away, and that goes with like just investing in general. To be fair, like initially, a lot of people who are not as knowledgeable and not as well read about it tend to lose money, and that's again my experience. I don't know about the data on this, but that's what usually happens. And I feel a lot of people should get educated about this, and this is just another means of educating people about it. So yeah, it should be better, I guess, with time.
Okay. And I think that is sort of aligned with Marion's question. Marion says, "Thank you for your talk, Neel. You have extensively explored the benefits AI can provide to the financial sector, but which issues do you think could arise from it?" So I think that's sort of a similar question.
Mm-hmm. What issues could arise from it? I feel compliance is one big issue, stopping a lot of companies from actually implementing a lot of these things. Because it's not that we don't have these technologies yet, or that because institutions and businesses are the first to get these technology, get their hands on these technology, because it's a way of actually making more money out of it. I think compliance is one of the issues because, again, like I think 2 years back there was a Senate hearing with Mark Zuckerberg and the senators in Congress, and it was appalling to watch how less educated senators are about things like the internet, which has been around for like 2 decades. So I won't be surprised if making appropriate legislation on AI takes longer than you actually think it does. So that is one of the problems I foresee. And I think, as I said at the beginning, that there is already issue with emerging economies with bureaucratic footholds that is stopping banking and fintech companies from actually exploring all forms of all dimensions of technology and actually applying them.
Do you think that the apps that are available fairly recently, such as, well, I won't mention names, but there are apps that you can download on your phone that you can put as little as £5 or something into investments. Do you think that could help students or other people to educate themselves about trading?
It could perhaps, yes. I'm not too sure how just having access to those apps directly relates to how much of an incentive you take to actually educate yourself about it. I feel it can act both. It's a double-edged sword. It can act as a way to like be careless about, because it's just so easy nowadays to just deposit money into a trading account and just start. I mean, after verification and all the other all the time it takes for verifying your account and stuff like that. After that, just putting money into that and just start trading. And the fact that you can't actually physically see money, like a lot of the money that we have in circulation right now, you can't see it. So you're less emotional about it in a sense. So you tend to get a bit more careless than usual. So yeah, that is one of the things that I've personally noticed, and there's some kind of research on that as well. How people are more reckless with their credit cards than they are with physical cash. So yeah, that again, as I said, it's a double-edged sword. On one hand, also makes things easier for people. So why not?
Okay, great. There's no more questions on the live chat. If you do have another question, if you're watching and maybe through my talk you want to write it down, then I'll have a look at the end and ask you, Neel, as well.
Yeah, sure.
Okay. So we'll move on to my talk then, which is on convolutional neural networks, image classification and symmetries. So thanks. So I will be talking about image classification, giving an introduction to it and what sort of concepts we have to consider for that, and a bit about CNNs, the structure of them, and a bit about how they work theoretically. And then we'll look at convolution layers, which is a particular layer within the network, and look at some examples of convolutions. And then we'll finish finally on symmetries. So this presentation that I'm giving, so I'm a second year maths student, so this presentation will be about my second year essay that I will be finishing hopefully soon. It's been too long. But yeah. Next slide, please. So we'll start with an introduction. So the problem of image classification is an example of supervised learning. So given an image, like this one of a cat, the image classifier processes that image in some way to produce an output, which represents the image class or label that the image classifier predicts for that image. So, for example, this prediction would be a cat. And whether that prediction is correct or incorrect. Through a training process, we try and get better at the accuracy of this classifier. So over time, rather not over time, but given more data, then hopefully we'll get better predictions. Next slide, please. So the problem of image classification, so we can break the problem down into mapping from images to a space of labels. So there's a possible set of labels such as a set of animals, and so we might give a 1 to what the label, the classifier predicts for it, and 0s for the predictions where the image doesn't belong to that class. And next slide, please. So we may instead use a probabilistic representation, which gives us a bit more information. So how we could interpret these numbers as how confident is the classifier in its prediction. So of course, high numbers, we would like to say that the classifier is pretty confident. So we might optimize not just the accuracy of the predictions, but also the confidence. Next slide, please. So in general, given an image, we assume there to be a true underlying function f that maps images to labels. So given an image x, there's a function f that would take that image to a label f of x. And that's our target for this supervised learning problem. We're trying to approximate are functions that the classifier parameterizes approximate as close as we can to the function f. Next slide, please. And that's a visualization just showing that the images might be in some space. So because we have to break down the image into a form that computers can process, we have to represent the image as an array-like data structure. So for example, we can represent each pixel of an image by their brightnesses in each color channel. So for example, red, green, and blue. Another way might be using a Fourier transform. Next slide, please. So the target function could be visualized like this. In high dimensional problems, visualization is limited, but we can imagine that we have certain regions in our domain space, so the domain of F, where the images are. So this is the space of possible representations of the images. And those certain regions are the pre-images of each label. So given, say, the label cat, of course, then you can see that there's some region in the domain space of images where all these images inside that bubble are mapped to the label cat. They may, of course, not look like bubbles at all. They might look disjoint and completely not smooth at all. But we'd like to assume that there's some property that we can find. So next slide, please. We'd like to assume that there's some way where we can transform the images in each of those pre-images. Sorry, I realize that images and pre-images are quite confusing when spoken about together. But imagine if we are in that cat bubble and we give it some transformation. So we apply a rotation or a translation, and we'll see more examples of possible transformations that we could make. And we could apply those transformations smoothly so that we stay within our pre-image of cat. So we are essentially thinking about the level sets. So this is mathematical term if you don't know. So level sets are essentially similar to pre-image. I won't go too much into it, but we'd like to make a smooth transformation and we'd stay within that bubble. Next slide, please. So take a look at the image of cat again. So I've transformed the image with some artistic effects, just using PowerPoint. But we can still say that the images are of cats. So given the label space being cats, dogs, foxes, etc., then the output of the true underlying function f should still be cat for all of these images. Yeah, next slide, please. Yeah, so those images are still within that pre-image of cat. And we could vary the transformations smoothly. So a similar transformation to ones on the last slide is something like this, where we are varying the contrast. And
sorry about that.
Okay, No worries. So we are varying the contrast smoothly, and we are still within the pre-image of cat. So there are various transformations that we could make, and we'd like to know what those are. So next slide, please. We could also rotate the image smoothly and still remain within the cat's pre-image. This would mean that the target function f, again, is invariant under the rotation group. So the rotation group is just a set of elements representing rotations that, when applied to the images, we are still being... we can still say that these images are of cats. So, next slide, please. And another example is translation. So, the target function would again be invariant under the translation group. And that's the focus of my second year essay. Next slide, please. So along the way, from the capture of photons to storage of the image to prediction, there are various sources of error. We would like, ideally, to have our computer learn a deep understanding of what a cat really is, like we do, so that it can cut through noise in distortion and pixelation and predict the label correctly. These errors might occur separately. For example, we may have a low prediction error, but we might be overfitting to noisy images. The pixels in the image we are training on, our classifier on, may be very dense. But a question we could ask would be, could the classifier predict correctly given more pixelated images? Next slide, please. So now we'll return our attention to CNNs, or convolutional neural networks, which are layer structures that produce approximations to our target function in the context of visual data. So here is a visualization of what a CNN might look like. So the first few layers are convolution and pooling layers, which are then hooked up to a sequence of fully connected layers. The final layer then gives the classification. Next slide, please. So the convolution layers are responsible for extracting features from the image. So as the example at the bottom of the screen shows, in the early layers, the features are relatively low level, so edges and outlines. Then they build up in later layers to more high-level features, such as eyes, noses, and eventually faces. The pooling layers reduce the number of parameters that define each approximation to our target function f. They also make the approximations closer to being translationally invariant, so invariant under the translation group. I show in my second year essay, I'm aiming to show that strided convolutions also do the job of becoming more translationally invariant. Fully connected layers make up the final layers, and they learn a mapping but from feature maps to classes. So for example, trained on images of cats, these features might be ears, eyes, and noses. the fully connected layers map those features to the classes of the images where they seem to fit well. Next slide, please. Okay, so we'll now look at convolution layers a bit closer. So part of the convolution layer is the convolution operation. The convolution operation is just taking two matrices. Say from this example, we've got a somewhat bigger matrix on the left and a much smaller matrix on the right. The one on the left might be the original image representing the pixels, or it could be the result of a previous layer, which we would say it's a feature map. So in general, I'll just say it's a feature map. And the smaller one is called a filter. So what it does is we overlay the filter on top of the feature map. Next slide, please. And the result of the convolution on that area is all of those elements multiplied together component-wise and then summed up. So we've got we've got a result of 0. Next slide, please. And then we can do that again, just shifting the square over to the right on the feature map, and we'll do the same operation again. And moving to the right, so next slide, and again, and again. So we'll then complete the final matrix, and then that's the result of the convolution operation. So we can kind of say in this example, the filter is a feature extractor. So what feature is it extracting exactly? It's extracting a vertical edge, which in particular a vertical edge going from bright to dark. So 1's representing bright and 0 representing dark. So if we flipped that, so next slide please. Yeah, so if we flip that, we'd expect something like this. Next slide please. So here we have the results where in the middle of the resultant matrix we've got negative numbers, which represent that it's the opposite of what the filter was looking for. Next slide please. So if the filter doesn't find anything like what it was looking for, then, such as a horizontal edge, then it's going to return just zeros like this. Next slide please. And you could rotate the filter if you wanted to get a resultant matrix like this. Next slide please. Okay, let's see an example. So Setosa.io is a website that Connor, who's present, he shared with me very kindly. So if you scroll down, please. Okay, I think we'll have to upload the... Oh, no, don't worry. Yeah, okay. So this is kind of similar to the filter we were looking at. A left Sobel is pretty much the same filter, except it gives a bit more emphasis on the center the center elements, and this is the result. So it's extracting particularly the left edges. So if you scroll up, maybe we can have a look at this one. Yeah. So you can sort of drag your mouse over the input image. Maybe we could change the kernel, which I've just called the filter. Something like outline. That's interesting. Okay. So yeah, so this is of course trying to find outlines. Okay. Let's go back to the slides. Next slide, please. Okay. So now the focus of my essay is on the symmetries of convolution layers. Next slide, please. And in particular, on translation. Next slide, please. So here, as we saw on Setosa, for a grayscale image of a cat with the left Sobel filter, we get a feature map like this. And we could translate the input image, which is the one on the left, just to the right. So next slide, please. And the feature map is translated pretty much exactly. It should be exactly the same translation. And you can sort of flick back from the previous and next. So just no. So just do left, right, left, right. Yeah, exactly. So this is a property of convolution layers called translational equivariance. So this means that when we vary the image by a certain amount in a particular direction, then the feature map varies exactly the same way. Okay, next slide, please. So now we'll look at another type of convolution called strided convolutions. So in this particular example, we'll have a stride of 2. So we'll set up our matrix again. I've had to change the size of the input feature map just a little bit, but don't worry too much about that. Next slide, please. So as again, we'll multiply all our components together, sum them up, and we get a result of 0 for this square. And then next slide, please. And then we'll take a stride of 2. So instead of moving to the right of just 1 square, we'll move to the right with 2 squares. And also, when we move down, so when we complete the lower rows of the matrix, then we'll move down 2 as well. Next slide, please. And again. Yeah, so we're taking another stride of 2 to the right. Keep going. Yeah. So that's our final matrix. And again, we can see that it's extracted a vertical edge from bright to dark in the middle of the image. Next slide, please. And in general, we can have a stride of S. And in this particular example, S equals to 2. Next slide, please. Okay, just a slide with a cat in it. I can't remember why. Next slide, please. Okay, right. So in my essay, I try to give a proof that if you give the convolutional neural network a sequence of strided convolutions, one after the other, so you'll get closer and closer to translational invariance. So if you next slide, please, and again, yeah. So what I'm aiming to do in my essay is to give a proof that as the number of strided convolutions increases, the closer the CNN gets to invariance of translation. So that means that if it has an infinite number of strided convolutions, then we'd hope that if you translated the input image, as much as you like, then if the original prediction was a cat, then the resultant prediction would still be cat. There's a lot of assumptions with this theorem that I'm trying to prove, and one of those is that there's no bound of image. So in my previous examples of translation, when I translated the image to the right, then of course some of the image would be cut off, and if you keep going, all of the image would have gone. One of the assumptions of the theorem is that there is no bounds like that. You can look at the infinite grid, and you'll still be looking at an image of a cat. That's essentially what it's trying to do. But the upshot of that theorem is that small translations where the cat is still within the image, it says that we can still predict that the image is a cat. Next slide, please. So some references. So these are references that will go in my essay as well. And I found group equivariant convolutional neural networks particularly useful, and it goes more into a particular type of convolutional neural network called GCNNs, which try to develop more equivariance to other types of group operations other than translation. So they focus on rotation in particular. But there's a lot of research that has happened where they've tried to, researchers have tried to vary other things like contrast, lighting, brightness, all sorts of things, and also in 3D as well. So not just in images, but of 3D images, where you can still use a convolutional neural network, and you're still hoping for properties of the underlying function f to remain within the approximations, such as changes of lighting, you should still be able to detect objects. You should still be able to predict correctly within some bounds. So if the brightness goes too dark, then yeah, maybe that's where you stop. Okay, next slide, please. I appreciate that without visualizations, my explanation was not the best, but that's it from me. So, thank you very much for watching. I'll just check the live chats to see if there's any questions. Okay, Charlotte says, what do you think is the most exciting application of CNNs? Ooh. I think an interesting application of CNNs is when it's used not just on images, when it's used, for example, to classify someone's voice in a recording, or song classification. When you're trying to find out what the song you're listening to is, and I think that's particularly interesting because it's still similar to an image classification problem. It's just that you have to make the image from the sound data. So the sound data is going to be something like a graph of volume, amplitude, of frequencies. And so you can take this data and you can kind of look at it visually. So you can compare what you're listening to, its sound graph, compare that to a known song in a database. And comparing sound graphs gives you your prediction. So that could be an interesting application. Other applications, I'm sure there are loads. I mean, CNNs are probably one of the most powerful type of neural network out there, and they can be applied to so many different things. And again, it doesn't have to be visual. At least explicitly, in the same sense of sound data. It's not explicitly visual, but you can make it visual. So Connor says, why is data augmentation using these translations good for the CNN accuracy? So I'm not particularly sure about translation, but so the focus of my essay was looking at the image classification invariance problem separately from data augmentation. So I was saying I know that data augmentation is a way of doing it, but I was sort of giving reasons why we use CNNs in the first place, rather than general feed forward, multi-layer perceptrons. And I guess you can kind of look at, say, rotation. Maybe it's computationally more efficient to augment your data rather than to introduce more layers, because at the end of the day, we can't really have an infinite number of convolution layers. we can't have a very big number either, because at some point it's just going to be too computationally expensive. And the whole reason why we're using CNNs in the first place is to reduce the size of our parameterizations. We want to produce complicated approximations to our function f without too many parameters, without too many numbers to fiddle around with. So that could be an argument for augmenting your data rather than introducing another layer. So I hope that answers your question. Or other things like rotation. Yeah, so Ariel says, can CNNs be used to look at climate change? Yeah, I was thinking of that as an answer to the other question from Charlotte. I'm pretty sure they can. I'm just trying to think of. Okay, so I guess when you're looking at climate data, you can always make it visual. So you can look at world maps of temperature, of pressure, and so on, rather than just looking at one number, global temperature or global average temperature. It may be better to look at several images of the world map at a certain time, maybe averaged over a year. And so you might want to ask the questions, what does climate change look like? Is this actually climate change, or is this something that's we should be able to expect? So looking at that as a classification problem, then maybe CNNs could be used for that. Yeah, maybe. Okay, if you got any questions, any more questions, then feel free to put them in the chats. Otherwise, that's it from me. Thank you very much, Neel, for presenting today.
No problem. Thank you for your time.
Thank you for watching, and keep up to date with our social media for our coming roles for next year. I hope you apply, if you're interested, and good luck if you are applying. Thank you very much.